Hi, good afternoon. Sorry I'm late drawing my beautiful picture here. Let me just finish this up. Okay. Today and Monday, I'm going to be talking about MapReduce, which is a software algorithm invented at Google that is now very widely used for handling large collections of data out in the world. By large, I mean very large, internet-sized collections of data. So the plan is, today I'm going to show you not using MapReduce, but sort of doing on a single computer what all the steps are in a MapReduce. And then Monday we're going to look at the real thing. And what we have, the implementation of this algorithm that we're using is called Hadoop. It's an open source version that originated at Yahoo, but a lot of people have worked on it. And some of your predecessors as students have created a scheme interface to Hadoop. Hadoop itself is done in Java, and you'll be seeing that in 61B or C. But here we're going to show you the functional scheme version. So first take a look at this picture, which is about something that we do all the time, just in plain old single computer functional programming. By the way, we're in a way back in the realm of functional programming, although the actual MapReduce is not purely functional. It does things with sequential programming and mutation. And in particular, one of the things we're mutating is files on a distributed disk file system. So we're given an input file, and we produce an output file. So in that sense, this is not functional, because that's a kind of permanent product of running MapReduce. But let's start just with the very, very simple thing that you've done a million times before. Accumulate some function and some base value, the result of map some other function on the data. So let's see if I can start up a terminal here. Yeah, so suppose I say accumulate plus map count Okay, so the first piece of that, it's just this. If I copy that and then paste, we get, for each word of "got to get you into my life," how many letters that word has. And then we say, okay, add those all up, and the sum is 21. Okay? So that's a simple example of take some data, manipulate each value, each individual value in some way. That's the map part. And then do some kind of accumulation of the result. Okay? And that's... that turns out to be useful not only in little toy problems like the one I just did, but in great big problems where you're trying to, let's say, compute page ranks or something. You've got all the data from all the internet stored on your disk because you're Google, and you want to take each web page and compute some function of that web page and then combine the results so as to get some useful information. Okay? But when the amount of data is huge, we can't really do it in the functional way in which we have all the data in a great big list in the computer's memory, and then map produces another great big list in the computer's memory, and then we accumulate the results from that. That just won't work on, industrial-sized data. So you already know part of the answer to that, namely streams, right? Streams are what you use if you have huge amounts of data, even infinite amounts of data, although last time I checked, the internet is not yet infinite, but it's pretty close. So we're going to use streams in our MapReduce interface. And the other idea that's important that we're going to use is the notion of a key-value pair. So you've seen this before in association lists, right, for tables. So you have a table that's organized by keys, and you want to be able to find the value associated with the key. So it turns out that MapReduce is most useful if what you're dealing with is key-value pairs. So in the simple version, there's just one map that goes through all of your data one at a time. So, minimum theta of n time, right? Supposing it takes constant time to process one datum, and there's n of them, it's going to be theta n time. So now you have to imagine that we have a number of computers. In your case, I think the number of computers is going to be 12 or something like that when you do it in the lab, more or less. But in industry, it would be more like 1,000 or 10,000 computers. And each one of them gets some key-value pairs. These key-value pairs are not in any particular order. So the way they're distributed among processors is that, separate from MapReduce, we also have a distributed file system. So you can have something that you think of as one file that actually has part of it on this computer and part of it on that computer and part of it on that computer. So basically, to a first approximation, each computer handles the data that are already on its local disk. Sometimes it's more complicated because you have a computer that doesn't happen to have any of this file on its local disk, so it asks one of its neighbors to send it some data. So each of these maps takes the same mapping function, the function I'm calling F1 here and F1 there. It's the same idea. It's the function that's doing the mapping. It's called F1 for two reasons. It's a mnemonic name. It's not just a default name. It's F1 for one thing because it comes first. You do the mapping before you do the accumulation. Right? Reduce, by the way, is just another name for accumulate. You'll find them both out in the world. So first you do the mapping, so that's F1, is the mapper function. Not to be confused with map itself, which you know what that is. And then later on you do the accumulation using F2, which comes second. The other mnemonic significance is that F1 is a function of one argument. Right? When you call map, you have to give it a function of one argument as its argument. And F2 is a function of two arguments, because that's how accumulate works. Right? You take the value so far on one new element and you combine them in some way, because it's a combining operation that you're doing. So that's a two-argument function. So we take F1 and we apply it to one key-value pair at a time. And the result of that, what your mapper function has to return, is not a key-value pair, but a list of key-value pairs. And that's because a single input key-value pair might give rise to one output key-value pair, or more than one, or zero, because remember when we were working with higher order functions back in week 2, and later week 5, I guess, there were 3 of them, right? Besides map and accumulate, there's filter. And in the MapReduce protocol, the map stage can also do filtering. It can take an input key value pair and reject it so that nothing comes out. So what map returns for each element of the input is a list of key value pairs, possibly empty. The reason there might be more than one is, let's say the value of some input key value pair is a sentence. You might, because of the problem you're trying to solve, need a key value pair per word of that sentence in your output. So however many words there are in this sentence, that's how many key value pairs will be in your list. So that's different from the single processor situation where one input value gives rise to one output value. Here it gives rise to a list of outputs. And then, this is a part that people sometimes find confusing. MapReduce really should be called map sort reduce because there's a stage that comes next that isn't in the name, which is sorting the key value pairs to bring together all the ones that have the same key. So here we have individual key value pairs, and after the sort, we have one key having more than one, or maybe 1, or maybe 0, but no, 0 ones get eliminated. So at least 1, but maybe more than 1 value attached to that key. The confusing thing about this sorting is that there isn't a computer that sits there doing a sort, like insertion sort or selection sort or merge sort or any of those sorting algorithms. Instead, what happens is there's a function that you tell MapReduce that associates a particular key with a particular computer. So when a key value pair comes in, you compute f of that key, which is usually something pretty simple, like it could be the first letter or the number of letters or something. And then that tells you which computer to use for the reduction of that key. So you're kind of throwing values at the reduce process one at a time as they come out from the map stage. So the sorting happens kind of in between everything else and at the same time as everything else. So then what you do, if you look at the right part of that diagram, is you take the key values collection and you take the key and just put it on the output. So MapReduce itself handles the key part. And then each of the values associated with that key goes into the reduce process. So you're not reducing all the values in the world. You're reducing the values that have a particular key. And that's important because if you were reducing all the values in the world, you couldn't do that in parallel necessarily. That would end up being a bottleneck to the parallelization of this process. So each key gets reduced separately. And so what we end up with is not one value like the number 21 that I got up there, but rather a stream of key value pairs. And in the output from the reduce stage, each key just has one value associated with it. Sometimes that stream of key value pairs is exactly what you wanted. Sometimes you're going to have to do a further reduction to get down to one single global value. But instead of having, a million items of data to reduce over, you've got it down to, let's say, 26 if the key were the first letter. And reducing 26 things, that you can do on a single computer in not very much time. Okay, so it should be called map sort reduce. Okay, questions about that so far? Who's feeling happy, not happy? It's not too bad except for the hands that aren't up at all. Okay. So we should now try to look at some actual examples. Let's is this what I want? No. That's what I want. Okay. So the first thing we have is, yeah. Yeah. The question is about what happens after the sorting. And yes, in our MapReduce implementation, what you have is a key with a list of values associated with it. In the real MapReduce, which is a little different from this, the values don't turn up all at once. They turn up one at a time. And each reduce process waits for a new value to come in. And when a new value comes in, it computes a new accumulated value until finally all the data have finished. So in the real MapReduce, they don't actually make a list of all of them. They just come in one at a time. But in our version, yes. OK, so starting point, highlighted up there, we have an abstract data type called key-value pair with a constructor make kv pair and selectors kv key and kv value. kv for key value, if that isn't obvious. OK. And now, from this point on, what you're seeing is only to try to give you an idea. It's not, the actual parallel MapReduce at all. There's this function called group reduce that takes the F2 and the base value and buckets, which is a list of lists of key value pairs. And what it does, let's pull this up here. Whoops. So we map over the buckets, lambda of subset, make kv pair. So yeah, each subset, I'm sorry. What buckets is a list of key value lists, like what comes out of the sort. So it's all of those things in that column of key value, value, value combined. And so what we do is we do sequentially what would really be done in parallel, which is we take one bucket that's a key and a value that's really a list of values. So that one bucket is called subset in here. And we make a key value pair, which we take. I'm sorry, I was wrong. What we have in buckets is a list of key value pairs in which all the key value pairs with the same key are next to each other. So each one only has a single value. So we take kv key of car of subset, which is going to be the same as kv key of all the rest of them. So that's copying the common key into the key of the result. And then the value of the result is going to be accumulate map kv value subset. So map kv value subset gives us just a list of values, and that's what we accumulate. So we're simulating the fact that the key does not go through the reducer. In fact, the reducer doesn't know what the key is. It's just looking at a bunch of values, and it combines those into a single value. So that's the job of group reduce. We also have in this implementation sort into buckets. Sort into buckets says sort by key, so we get all the... Why are you doing this? Stop that. Thank you. So we get all the KV pairs with the same key next to each other, and then group is going to find all the adjacent KV keys that have the same key and form a list of those. So we start with just a list of KV values. We end up with a list of lists of KV pairs. Okay? And I'm not going to show you group, which is completely straightforward. You should be able to write that, even though it's long. Sort by key. I'm not going to go into the details either, except for this thing called super before. In order to sort, you need a way to say this comes before that, or this is the same as that, or this comes after that. Right? In the real MapReduce takes a bazillion arguments because you can fine-tune it to make it more efficient for your particular problem. We tried to simplify away most of that flexibility. And so to do that, we have one comparison function that we always use. And basically, the comparison function is, if we're comparing two numbers, then use a numeric comparison. If not, use an alphabetic comparison. Okay? That's the rule. And that's what all this says. Okay. Here's another abstract data type called a file. This simulates files in the file system. And a file consists of its name and the stuff in it. And we're taking the stuff in it as lines of text. Each line of text in a file will be represented by a sentence. Okay? All of the data in the cluster that you're going to experiment with MapReduce on next week, we have a bunch of data provided for you, including all the Shakespeare plays and all the works of Charles Dickens and all the names of Beatles songs. We're working on, it's kind of a stalled project, somebody may want to help out with this later, taking a snapshot of Wikipedia and making that readable by your programs. But we're not there yet. Anyway, so a file on the disk consists of its file name, which is a symbol, and lines, which is a list of sentences. Okay? So file to line list says take that file on the disk and turn it into a list of key value pairs where the file name is the key for all of them and the values are the lines of text. So let's say we have all of Shakespeare's plays. That's one file per play. So you'll have a file called, Julius Caesar and, the evil that men do live after them, the good is often interred with their bones. New line. So let it be with Caesar. Boom. I come to bury Caesar, not to praise him. Boom. Etc. Okay? That one actually probably comes first. Friends, Roman countrymen, lend me. This was like 10th grade, so a long time ago. Anyway, so file to line list is going to give us Julius Caesar, friends, Romans, countrymen. Julius Caesar, lend me your ears. Julius Caesar, I come to bury Caesar, not to praise him. Julius Caesar, for the evil that, etc. Okay? Never mind match, we'll come to that later. Okay, and here we have some sample data. Okay, so these are some fictitious 61A students and their midterm scores. And then we have file 1, file 2, file 3, where what comes first is the name of an album, and that's the file name. And what comes after that is names of songs, and that's the data. One song name per value. I don't have all of them. I only have 3. Okay, so suppose I say append MT1, MT2, MT3. I get this. So it's all CS61A something is the key, and some midterm score is the value. And by doing this append, I've lost the information about which midterm is which, but that's okay for my purposes. So now I'm going to actually do this. And let's see if I can. Oops. Hey. All right, let's just try this. Okay, that's good enough. All right, so this whole thing is a list of buckets. And a bucket, if we start here, goes to here. That's the data for midterm. No, that's the data for CS61A XB, who only took 2 of the 3 midterms. And here's the data for XC, who took all 3. Here's XD, who only took 1 midterm. Here's XF, XK, etc. Okay? So sort into buckets has sorted this data by student. And now let's see what group reduce does. So I group reduced using plus as the accumulator. And so what we now have is a list of key value pairs, 1 key value pair per student, only one, exactly 1 key value pair per student, in which the key is the login, and the value is the sum of the midterm scores. So XB, his scores were 40 and 32. That added up to 72. XC got 27 plus 25 plus 28, which turns out to be 80, and so on. Okay, questions so far? Yeah. Is this how your scores are calculated? Well, adding up your scores, yes. MapReduce, no. There aren't enough of you. Yeah. So a bucket is a bunch of key value pairs that have the same key. Okay, so we've sorted the key value pairs so that all the ones with the same key go together. And then, what was the name of the program that puts them in buckets? Let's see. Yeah, group. Group takes a bucket like that and makes it no, that's the result from group, is a bucket per thing. And that's what goes into the group reduce procedure. Takes a list of key value pairs that all have the same key. So the important part is that this group reduce models a bunch of reduces happening on different computers. Okay? So we only have 1 computer, but that's what is going to happen in actual MapReduce. So, oops, coming up here. Oh, yeah. Okay, so what I did here is I took a song title, Cry Baby Cry, not chosen randomly, and imagine that coming in at the left end of the diagram. And now what map does, and this is a map that's happening in parallel for all the different Beatle albums, is make a KV pair that has the word cry or baby or cry as the key and 1 as the value. Why on earth would we want a bunch of key value pairs that have 1 as the value? Because, that was a rhetorical question, because we are now going to accumulate those with plus. And that's going to tell us how many times the word cry appears, and how many times the word baby appears. So baby occurs once, cry occurs twice. Okay? Well, okay, let's look at file. It's a line list of file 1 and see what that actually does. It gives us Please Please Me, it's the album name. I saw her standing there. And then Please Please Me, Misery. And that's all I can read. So we'll. And then Please Please Me, Anna, go to, it's in a parentheses, go to him actually. Please Please Me, Chains. Please Please Me, Boys. Please Please Me, Ask Me Why, and so on. Okay, so key value pairs where the key is the album name and the value is a song name. So what good is that? So I'm going to take file to line list, so key value pairs like you just saw, for 3 albums appended together, and I'm going to call this procedure word counts. And we get this. And notice this is in alphabetical order. And that's because the sorting of keys onto reducers was, in this example, done alphabetically. Okay? So it's a long list. So the word love appears 4 times, tied with A. It's not actually the most popular word, which is going to turn out to be I with 7 occurrences. But, oh, me, all right. Me with 8 occurrences. So, I mean, you only has 7. So I guess that shows that the Beatles are more self-centered than is their image. So let's actually back up here and look at procedure word counts and see what it does. So it takes files, which is that appended list of files, and then we map. Have you seen flat map before? Yes. No. Who hasn't seen flat map before? Okay, we'll talk about it. For the moment, pretend it just says map. So what we're mapping is this function, which takes in a key value pair as its input, and it returns the result of a map, an inner map, which is this one, that maps over the values. So for each song name, no, I'm sorry. It maps over the values. The value is a song name. KV value of KV pair is one song name. So this function is mapping over the words of a song name. And for each word, we say make KV pair word 1. So, you know, love me do would turn into love.1, me.1, do.1. throwing away the album names. We don't care which album a song is on for this purpose. So we make a bunch of ones, and then we do sort into buckets so that all of the occurrences of A are next to each other, and all of the occurrences of me are next to each other, and so on. And then finally, we group reduce by addition, and that's how we got this list of word frequencies. And now, I can use that information to find out the most commonly used word. And that's done with an accumulate done on a single computer of the results of this process. So on a single computer, we compare results. I was able to do it on a single computer because this is a very small amount of data. If it was the works of Shakespeare, then there might be a lot of words. I mean, the elements of this list is still going to be only one per word of the English language, not one per occurrence of a word in Shakespeare. So it's not as much as you might be thinking. But how many words are in the English language? 50,000, I'm guessing? 100,000, something like that. A lot of words. You probably know some tens of thousands of words. And there's more in the dictionary that you don't know. I mean, that I don't know either. Okay, how are we doing on time? Brilliantly. Oh yeah, okay, pattern matching is what's next and last. Let me back up and just kind of review where we are. In these problems that I've been doing, and the programs are all in my lecture notes in the reader, and it will pay you to go over them more carefully than I can do in an hour. But we tease out explicitly 3 separate steps. So there's a map over all the data, and then there's sort into buckets that does that middle step, and then there's group reduce, and it's not just plain old reduce because we're not getting one overall result, we're getting one result per key. Okay? So that's what a MapReduce really is. It's a group reduce in parallel of a sort in parallel of a map in parallel. Okay? Let me pause for questions. Okay, nobody's going to come rushing up at the end of class to ask me questions, right? Okay. So let me show you match. Okay. Match is a procedure that takes 2 arguments. The first one is called a pattern, and the second one is a sentence. A pattern is a sentence, but some of the words in the sentence might be asterisk, and each asterisk means any 0 or more words. So star I star her star means I'm looking for a sentence that has the word I and the word her in that order, but maybe some other stuff, and the result of this match is true. So and I love her. It's also true. P.S. I love you returns false. Okay? Is that? Yeah.
There's no limitation on if there's one asterisk, there's one word.
No, each asterisk can match any number of words. So if you think about how this match procedure actually works, which I'm completely skipping over for now, but it's worth you looking at, because of that fact that each asterisk can match a variable number of words, and we don't know ahead of time how many, this actually is an exponential time computation. But luckily, the way this is going to work is that although we're going to call match a lot of times, each match is dealing with a short sentence. So it doesn't matter that it's exponential time over n equals 5. So that's okay. So using match, I have this procedure grep. Grep is the name of a Unix utility program that you should know about if you don't. It says search for a pattern in the lines of a file. And so I'm looking for star I, star her, star in all these Beatles songs that I have. And the result is, no, this is right. So the result is a set of key value pairs where the key is the album name and the value is the song. And for these 3 albums, the only ones that matched are And I Love Her and I Saw Her Standing There, which are the examples I showed you before. And all the other Beatles songs on these albums did not match this pattern. Okay? So you can see that this is actually pretty useful. The ability to look at a lot of data and select values, lines of text for us that include, certain things in certain combinations. We being Dan Garcia and I are writing a proposal to the NSF to get a lot of money to help disseminate CS10, which is the beauty and joy of computing. So everybody tells us that proposals have to have good acronyms. So I used grep, the Unix grep, yesterday to search for English words that have the letters BJ consecutively in them. And so our proposal is called Frabjous CS. Okay, so that's the last example I'm going to show you. I hope you get the idea of how some of this can be useful. I'd like you also to get the idea about this trick of using a value of 1 out of map for everything, and then using plus to count things. That's something that is comes out of the Google paper. The Google paper that introduced the MapReduce algorithm is in the reader. You should read it. It's interesting. Let me, in the 3 remaining minutes, tell you that problems for parallel computation come to a first approximation in 2 flavors, easy and hard. And the easy ones are the ones in which the data decompose in an obvious way. So you're doing a lot of computations, but on each datum in isolation. MapReduce is great for easy parallel problems. Parallel algorithms is a topic of a lot of research right now, and the researchers aren't thinking about the easy problems, they're thinking about the hard problems and how to make those manageable. So people who are really parallelism researchers say, oh, MapReduce, trivial. But it's the starting point for everybody in studying how this works, because when the Google guys invented MapReduce, they looked at all the programs that they were running every day and found that some huge percent, like 2/3 of them, were expressible in terms of MapReduce. And I should have said this at the beginning, but here's why that's important. Let's say you have a great big problem and you're trying to solve it on 10,000 computers. So you've got a great big warehouse someplace that has racks and racks of PCs hooked up in them, okay? And even with all this parallelism, this program is going to take all day to finish, right? Because the internet is huge. What's going to happen during that day with 10,000 computers? You guys aren't sysadmins. One of them is going to die, right? You know, your computer dies every less than 10,000 days, probably. And one computer for 10,000 days is like 10,000 computers for one day in terms of the probability of failure, which is very, very, very high. So it used to be, in the bad old days at Google, that every programmer had to build into every program a lot of code for what to do when a computer fails, how to find out that a computer has failed, and how to redistribute its work among the other computers. And that was so, so hard that you had to be a genius to do 2 + 2 at Google scale. And they could only hire genius programmers. MapReduce buries all that under an abstraction layer. So the MapReduce program itself worries about how do we divide the problems among the computers, what do we do when a computer fails. All of that stuff is written once and for all. And that means that ordinary people like me, most of you, can do parallel processing on a large but not complete set of problems. Okay, Monday we'll look at the real thing. Have a good weekend.